Have you ever, paused to wonder how a simple aspirin tablet works its magic? How it reduces a fever, or maybe what gives a freshly cut pineapple that really distinctive sweet scent? Well, today we're diving deep into the fascinating world of organic chemistry, specifically Chapter 20 from David Klein's Organic Chemistry, third edition. It's all about carboxylic acids and their derivatives. Pretty interesting stuff.
That's right. And, for a lot of students, this chapter can initially feel a bit overwhelming, like just a huge list of reactions you have to memorize. But our mission really for this deep dive is to cut through all that complexity. We're going to uncover the core idea, the mechanistic principle that actually ties almost all of these reactions together. It's called nucleophilic acyl substitution. And honestly, understanding this one key concept, it'll dramatically simplify your learning, less rote memorization, and you'll actually see the bigger picture, the elegance of how these molecules work.
Exactly. And when you grasp this fundamental principle, you'll start seeing how it explains, well, everything from how aspirin functions, like you said, to the structure of proteins, even how everyday soap is made. Get ready for some serious aha moments, I think. So, okay, let's unpack this a bit. What exactly are carboxylic acids? At their core, they're organic compounds defined by having a Mansu-A-COH group. Simple enough, right? But what's often surprising is just how, well, everywhere they are in nature, they're behind so many familiar odors. That sharp tang of vinegar, that's acetic acid, the smell of rancid butter, butanoic acid, even, dirty socks, hexanoic acid. And sour milk gets its tartness from lactic acid.
And beyond those everyday smells, carboxylic acids are, profoundly important in the pharmaceutical world. We rely on them for essential medicines like acetyl-salicylic acid, which everyone knows as aspirin. Then there's 4-aminosalicylic acid, a really crucial treatment for tuberculosis, and isotretinoin for severe acne. Plus, think about industry. The U.S. alone makes over, 2.5 million tons of acetic acid every year, mostly to make vinyl acetate, which is key for paints, adhesives. So yeah, they're not just like textbook examples. They're fundamental to so much of modern life.
Right. And when it comes to naming them, the system is actually pretty logical. For simple chain, a monocarboxylic acid, you take the parent alkane name, drop the E, and add oic acid. And you always number the carbonyl carbon as number 1. If the OACOH group is attached directly to a ring, we use the suffix carboxylic acid, like cyclohexanocarboxylic acid. Makes sense. And yeah, you'll definitely want to remember a few common names that just pop up all the time. Formic acid, acetic acid, benzoic acid. Those are key. For diacids, compounds with 2 carboxylic acid groups, the suffix becomes dioic acid. Think oxalic acid, malonic acid, succinic acid.
Yes.
You see these a lot in biochem.
Absolutely. And before we dive deeper into their unique properties and reactions, it's probably worth just a quick mental refresh on some basics. Make sure you're comfortable with, general mechanisms, pushing arrows, nucleophilic attack, knowing what makes a good leaving group, the basics of proton transfers. Sections 6.8 and 6.1 in Klein cover those well, because these are really the fundamental moves, the rules of the game for all the more complex reactions we're about to discuss.
Got it. So structure and properties next. The carbon atom in that XeOH group, it's sp2 hybridized, meaning it's got that trigonal planar shape, bond angles around 120 degrees. That's pretty standard for carbonyls. But what really makes them stand out is their intermolecular forces, right?
Exactly. This is pretty cool. Carboxylic acids can form 2 hydrogen bonds with another carboxylic acid molecule. They basically pair up, forming what we call a dimer, like they're holding hands. And this really strong pairing explains their surprisingly high boiling points. Take acetic acid, it boils at 118 degrees Celsius. Compare that to ethanol, similar molecular weight, which boils way down at 78 degrees Celsius. Those extra hydrogen bonds just lock them together much more tightly. It takes more energy to pull them apart into gas.
And while the name says it all, carboxylic acids, they are indeed mildly acidic. So if you put them with a strong base, like sodium hydroxide, they'll readily give up that acidic proton. They form a carboxylate salt. Naming's easy too. Just change benzoic acid to 8. So benzoic acid becomes sodium benzoate. You see that on food labels sometimes as a preservative. In water, they set up an equilibrium, right, between the acid and its conjugate base, the carboxylate ion. And the pKi values usually fall between 4 and 5, which means the equilibrium mostly favors the undissociated acid form in plain water.
Right. And just to put that in context, compared to strong inorganic acids like HCl or sulfuric acid, yeah, they're weak. But compared to most other organic compounds, especially alcohols, they're way, way more acidic. Acetic acid, for example, is something like 100 billion times more acidic than ethanol. That's, 11 orders of magnitude? Huge difference. And the why behind it is resonance stabilization of the conjugate base. That carboxylate ion, remember resonance, it spreads electron density out. Here, the negative charge isn't just stuck on one oxygen atom, it's delocalized, shared equally over both oxygen atoms. And that makes the carboxylate ion much, much more stable than, say, an alkoxide ion from an alcohol.
Okay, and that acidity becomes super important when we think about biological systems, right? Like at physiological pH, around 7.3.
Oh, absolutely. What's fascinating here is, given their pKe is around 4 to 5 at a physiological pH of 7.3, well, carboxylic acids exist almost entirely as their carboxylate salts. The ratio is something like 1,000 carboxylate ions for every one undissociated acid molecule. It's huge. Think about pyruvic acid in your body. It's almost exclusively present as the pyruvate ion, playing these vital roles in metabolism. And another really key aspect of their acidity is how it's affected by other groups on the molecule substituents. If you have electron-withdrawing groups, like, say, chlorine atoms nearby, they actually make the acid more acidic. They pull electron density away through the sigma bonds. That's the inductive effect, which helps stabilize the negative charge on the carboxylate conjugate base. And the closer that group is to the NaCOH, the stronger the effect. Conversely, electron-donating groups can actually destabilize the conjugate base a bit, making the acid less acidic.
It's interesting. Okay, so we've covered the structure, properties, acidity. How do we actually make these things? We've touched on some methods before, like oxidizing alkynes or primary alcohols or even alkyl benzenes, but this chapter brings in two really powerful new ways, and they're cool because they let us add an extra carbon atom.
Yeah, these are great tools for synthesis. The first one is the hydrolysis of nitriles. So you take a nitrile that's a compound with the C-triple bond N, a cyano group, and you treat it with aqueous acid and heat. That cyano group gets converted directly into a carboxylic acid group, COOH, which gives us this really neat two-step way to turn an alkyl halide into a carboxylic acid with one extra carbon. First step, SN2 reaction with cyanide ion to make the nitrile. Second step, hydrolyze the nitrile. Boom. The second new method is the carboxylation of Grignard reagents. You take a Grignard reagent, react it with carbon dioxide, dry ice is often used, and then you protonate the result with acid. Basically, the Grignard acts as a nucleophile, attacks the CO2 carbon, forms a carboxylate intermediate, and then protonation gives you the carboxylic acid. Again, a fantastic way to add exactly one carbon atom and end up with a carboxylic acid. Super useful.
Okay, so making them. What about reacting them? Carboxylic acids themselves, what do?
Reduction is a big one, right? Turning them into alcohols. Yes, reduction is important. The main reagent for that is lithium aluminum hydride, LiAlH4. It's a very powerful reducing agent, a strong nucleophile, and also a strong base. The mechanism is kind of interesting. It usually starts with deprotonation to form the carboxylate, then hydride attacks, reducing it to an aldehyde intermediate. But here's the thing, you can't stop there. LiAlH4 is so reactive, it immediately attacks that aldehyde again, reducing it further all the way down to the primary alcohol. You can't isolate the aldehyde.
Ah, okay, so it goes all the way. Is there a way to be more selective?
There is. Borane, BH3, is a great alternative. Borane is special because it reacts selectively with carboxylic acids, but it generally doesn't react with other carbonyl groups like aldehydes or ketones under the same conditions. So if you have a molecule with multiple carbonyls and you only want to reduce the carboxylic acid part, BH3 is your go-to reagent. Big advantage sometimes.
All right, let's shift gears a bit now. We've talked about carboxylic acids themselves, but a huge part of this chapter is about their derivatives. These are compounds where the aldehyde group of the carboxylic acid gets replaced by something else, right? But the oxidation state of that main carbon stays the same.
Precisely. That's the key idea. And the four most common types you'll encounter constantly are acid halides, like acid chlorides, acid anhydrates, esters, and amides. We also tend to include nitriles in this family because, well, their reactivity patterns are very similar and they can be interconverted with these other groups. The common thread is that central carbon atom having 3 bonds to electronegative atoms, usually oxygen or nitrogen or a halogen, that keeps its oxidation state consistent.
And it's pretty cool where these show up in the real world. Acid halides and anhydrides, they're super reactive, so you don't find them much in nature. Makes sense. But esters, much more stable, much more common. They're often responsible for those nice smells of fruits and flowers. Like methylbutanoate gives pineapple its scent. Isopentyl acetate is bananas. Butyl acetate is pears, that kind of thing. And amides. Well, amides are everywhere in living things. They form the peptide bonds, those repeating linkages that literally build all proteins.
And that brings us to a quick medically speaking point about amides. Amide groups are actually a really common feature in many drugs that act as sedatives. Think about melatonin, or drugs like zolpidem Ambien or Zolpidem Sonata used for insomnia. Even benzodiazepines like Valium and Ativan for anxiety, they contain amide functionalities. And research shows that while maybe not absolutely essential for the drug to work, having that amide-mide group often significantly boosts the potency of these agents.
Wow, okay. So how do we name all these different derivatives? Is it systematic like the acids?
It is, thankfully. For acid halides, you replace the ital acid ending with yl hali, so benzoic acid becomes benzoyl chloride. For acid anhydrides, you just replace acid with anhydride. Acetic acid gives acetic anhydride. If it's made from two different acids, an unsymmetrical one, you name both alphabetically. Esters are named in two parts. First, the alkyl group attached to the single bonded oxygen, then the name of the acid part, but change italic acid to ate, like ethyl acetate. Amides change ic acid or oic acid to amide. If there are alkyl groups attached to the nitrogen, you use N as a locator, like N-methylacetamide or N-dimethylacetamide if there are two. And finally, nitriles. You generally replace ite acid or oic acid with onitrile. Acetic acid relates to acetonitrile, benzoic acid to benzonitrile.
Okay. Our naming Now, here's where it gets really interesting. You said this is the core of it all, right?
Yeah.
Why do these derivatives react so differently? Acid chlorides are super reactive, and amides are pretty stable. What's going on?
This is absolutely the heart of Chapter 20. There's a very clear trend in reactivity, or more precisely, in the electrophilicity of the carbonyl carbon. How much does it want electrons from a nucleophile? The order is acid halides are the most reactive, then acid anhydrides, then esters, and finally amides are the least reactive. Nitriles sort of fit in there too, reactivity-wise. And the Y comes down to this balance, this tug of war between inductive effects and resonance effects.
Okay, break that down. Inductive versus resonance.
Right. Let's take an acid chloride. Chlorine is very electronegative, so it pulls electron density away from the carbonyl carbon through the sigma bonds. That's the inductive effect, making the carbon strongly positive, very electrophilic. But chlorine isn't great at donating its lone pair electrons back into the pi system via resonance. The orbital overlap isn't very good, so the inductive withdrawal wins. Very reactive carbonyl.
Okay, that makes sense for acid chlorides. What about amides at the other end? Least reactive.
Now look at Gmades. Nitrogen is less electronegative than chlorine or oxygen, so its inductive pull is weaker. But nitrogen is an excellent resonance donor. Its lone pair overlaps really well with the carbonyl pi system. Nitrogen can handle a positive charge quite well. So this strong resonance donation effectively pushes electron density back towards the carbonyl carbon, making it much less electrophilic, much less reactive. And this strong resonance is also why the CN bond in amides has significant double bond character. It's planar, rotation is restricted, and the geometry is absolutely critical for protein structure and function. It's not just about reactivity.
Wow. Okay, so that explains the reactivity trend. And you mentioned a unifying mechanism, nucleophilic acyl substitution.
That's the one. It governs nearly all the reactions of these derivatives in this chapter. It's similar in a way to nucleophilic attack on aldehydes and ketones. You have an electrophilic carbonyl carbon that gets attacked by a nucleophile. But the huge difference is that carboxylic acid derivatives have a group attached to the carbonyl, the halonide, the alkoxide, the arene part, that can actually leave. It's a potential leaving group. Aldehydes and ketones generally don't have that in these contexts.
So what are the steps?
Two main steps. First, nucleophilic attack. The nucleophile hits the carbonyl carbon. The carbon goes from sp2,2 trigonal planar to sp3 tetrahedral, forming this tetrahedral intermediate. Second, loss of the leaving group. That tetrahedral intermediate isn't usually stable. It collapses. The electrons kick back down to reform the CO double bond, and the leaving group gets expelled. The carbon goes back to sp2. And a really crucial rule here. Hydride ions and simple alkyl groups like CH3 are generally not viable leaving groups in these reactions. That's why aldehydes and ketones don't typically undergo substitution this way. They usually undergo addition.
Right, they don't have anything good to kick out.
Exactly. And another key point, unlike, say, an SN2 reaction, which is concerted, happens all at once, these two steps, attack and leaving group departure, happen separately. There's a distinct intermediate. Drawing it as one step is a common mistake.
Okay, attack then leave. Got it. What about protons moving around? You mentioned proton transfers.
Yes. Proton transfers are often essential pieces of the mechanism, especially under acidic or basic conditions. And there are rules of the game you need to follow. Rule 1. Under acidic conditions, you must avoid forming any strong bases in your mechanism steps. Think negative charges on oxygen or nitrogen, generally bad under acid. Rule 2. Under basic conditions, you must avoid forming any strong acids. Think positive charges on oxygen or nitrogen, or things like H3O plus, generally bad under base.
Okay, so how does that play out?
We'll take acid-catalyzed ester hydrolysis. Water is the nucleophile, but it's weak. And just having water attack the neutral ester carbonyl would create an intermediate with both a positive and a negative charge, not great. So under acid, the first step is usually protonating the carbonyl oxygen. This makes the carbonyl much more electrophilic, activates it. Now, weak nucleophile water can attack without generating an nasty intermediate. Then, before the alcohol part leaves, it needs to get protonated too to turn it into a good neutral leaving group, water or an alcohol molecule. You avoid kicking out a negatively charged alkoxide, which is a strong base.
I see. So the protons help make things happen correctly under those conditions. What about basic conditions?
Under basic conditions, say using hydroxide, OH, as the nucleophile, it's strong enough to attack the neutral carbonyl directly. No need to protonate first. The negative charge is just transferred from the hydroxide to the tetrahedral intermediate. Then the leaving group, like an alkoxide from an ester, can leave, and although it's basic, it's in a basic solution, so that's acceptable. Often there's a final proton transfer at the end to neutralize everything. So these proton transfers can happen before attack, before the leaving group leaves, or at the very end, depending on the specific reaction and conditions. You have to analyze each case.
Okay, that framework nucleophilic acyl substitution plus managing proton transfers seems really powerful. Let's apply it, starting with the most reactive. Acid chlorides. How are they made and what do they do?
Right. Acid chlorides are usually made from the corresponding carboxylic acid using thionyl chloride, SOCl2. It's a neat reaction because it converts the relatively poor leaving group into a really good one, and it produces gases like SO2 and HCl, which bedel away and help drive the reaction to completion, according to Le Chatelier. And because they're so reactive, acid chlorides are fantastic starting points to make almost any other derivative easily. You react them with water, you get back the carboxylic acid electrolysis. React with an alcohol, you get an ester alcoholysis.
Yeah.
React with ammonia or an amine, you get an ammonite ammonolysis.
For that amine reaction, you need extra amine, right?
Yeah. Yes, exactly. You need two equivalents of the amine. One acts as a nucleophile to attack the carbonyl, and the second acts as a base to soak up the HCl byproduct it forms. Otherwise, the HCl would protonate your amine nucleophile and stop the reaction. Acid chlorides can also be reduced. With a strong agent like LiL-H4, they go all the way down to primary alcohols, be it an aldehyde intermediate you can't isolate. But if you use a milder, bulkier reducing agent like lithium triterbutoxyaluminum hydride mouthful, I know you can actually stop the reduction at the aldehyde stage. Very useful.
Okay. And Grignards.
Grignards, RMGX react too. If you use excess Grignard, it adds twice, first forming a ketone intermediate, then adding again to give a tertiary alcohol after workup. But again, there's a way to stop halfway. If you use a Gilman reagent, a lithium dialcocuprate R2-silyate, it's less reactive and will add only once, stopping at the ketone stage. Another way to get ketones.
So versatile. Okay, next down the reactivity ladder. Acid anhydrides. Similar story.
Very similar story. Making them directly from carboxylic acids usually involves intense heat, which really only works well for simple ones like acetic anhydride. A more general lab method is to react an acid chloride with a carboxylate salt. It's another nucleophilic acyl substitution. Their reactions. Almost identical to acid chlorides. They undergo hydrolysis, alcoholysis, ammonolysis, all following the same mechanism. The main difference is the leaving group. Instead of chloride leaving, a carboxylate ion leaves. This means the byproduct is a carboxylic acid molecule, not HCl, so you usually don't need that extra base like pyridine when reacting with alcohols or amines.
And acetic anhydride is used a lot for acetylation.
Yes, it's a very common reagent for adding an acetyl group, CH3CO, onto alcohols or amines, which brings us back to aspirin, because that's exactly how aspirin is made. You take salicylic acid, which has both a carboxylic acid group and an alcohol H group, and you react it with acetic anhydride. The anhydride selectively acetylates the alcohol group on salicylic acid, forming acetylsalicylic acid aspirin.
And how does that work in the body?
Well, the aspirin molecule itself then acts as an acetylating agent inside your body. It transfers its acetyl group onto a crucial enzyme called cyclooxygenase, or COX. Acetylating the COX enzyme deactivates it. And since COX is responsible for making prostaglandins molecules that signal pain, inflammation, and fever blocking, it reduces all those symptoms. So it's all nucleophilic acyl substitution, first to make aspirin, then for aspirin to do its job.
Pretty neat. That is neat. Okay, moving down again. Esters. We find these everywhere. Lovely smells. How do we make them, besides from acid chlorides or anhydrides?
Good question. One classic way is the Fischer esterification. You take a carboxylic acid and an alcohol, mix them with a catalytic amount of strong acid, like sulfuric acid, and usually heat it up. The key thing about Fischer esterification is that it's an equilibrium process. It's reversible.
So you have to push it one way or the other.
Oh, exactly. To make the ester, you typically use a large excess of the alcohol, or you find a way to remove the water that's formed as a byproduct. That pushes the equilibrium towards the products, according to Le Chatelier's principle. Another way, mentioned briefly before, is using an SN2 reaction. You deprotonate the carboxylic acid to make the carboxylate anion, which is a decent nucleophile, and then react that with a primary or methyl alkyl halide. This adds the alkyl group via SN2.
Okay. And reactions of esters, hydrolysis is a big one, right? Saponification.
Yes, saponification is the term for ester hydrolysis under basic conditions. You treat the ester with a strong base, like sodium hydroxide or potassium hydroxide, usually with heat. The hydroxide attacks the carbonyl, the alkoxide group leaves. Now here's the clever bit. The carboxylic acid formed is immediately deprotonated by the alkoxide leaving group, and alkoxides are strong bases. This forms the carboxylate salt, which is resonance stabilized and unreactive towards nucleophiles. This deprotonation step is essentially irreversible and drives the whole reaction to completion. You then add acid in a separate step, workup, if you want the neutral carboxylic acid back.
And saponification, that's soap making, isn't it?
It absolutely is. That's the practically speaking connection. Fats and oils are triglycerides, tracers of glycerol. When you heat fats or oils with a strong base like NaOH, you saponify those ester linkages. You break them down, producing glycerol and the sodium salts of the fatty acids. And those fatty acid salts, with their long nonpolar tails and polar carboxylate heads, are soap molecules. It's the same reaction.
Amazing. Okay, what other reactions do esters do?
Well, you can hydrolyze them under acidic conditions, too. That's just the reverse of Fischer esterification. Again, it's an equilibrium, so you'd use excess water to drive it backwards. Esters react with amines, aminolysis, to form amides, but it's generally quite slow and not as practical as starting from an acid chloride. They can be reduced. LiOH4 takes them all the way down to 2 alcohol molecules, one from the acid part, one from the alcohol part. But similar to acid chlorides, you can use a special reagent, D-base, disobutyl aluminum hydride, usually at low temperature, to stop the reduction at the aldehyde stage. Very useful synthesis tool.
2 alcohols from LiOH4, but aldehyde with D-big. Got it. And Grignards.
Grignard reagents add twice to esters. Just like with acid chlorides, the first addition forms a ketone intermediate, which you can't isolate here, and then the second Grignard adds immediately, giving a tertiary alcohol after workup, with 2 identical alkyl groups from the Grignard. And this leads to another medically speaking angle, esters as prodrugs.
Prodrugs, what are those?
A prodrug is basically an inactive or less active form of a drug that gets converted into the active form inside the body, usually through metabolism. Esters are often used for this. Why? Maybe the ester form crosses cell membranes better because it's less polar than the corresponding acid or alcohol. Or maybe it allows for slow, sustained release. Examples. Dipephrine is an ester prodrug of epinephrine used for glaucoma. It crosses membranes in the eye better. Or think about long-acting antipsychotics like haloperidol-decanoate or bilipridone palmitate. These are long-chain fatty acid esters. They get injected, concentrate in fatty tissues, and are then slowly hydrolyzed over weeks, releasing the active drug gradually. Very helpful for patient compliance.
Fascinating strategy. Okay, let's move to the least reactive of the main group, amides, the backbone of proteins.
Indeed. Given their stability, making amides efficiently usually means starting from a more reactive derivative. The best way is typically reacting an acid chloride with ammonia, or a primary or secondary amine. Remember, 2 equivalents of amine needed. Starting from esters works, but it's slower.
Right. And thinking bigger picture, polyamides and polyesters.
Oh yes, the polymers. This is a huge,
Yeah.
practically speaking, area. If you take a molecule with 2 acid chloride groups, a diacid chloride, and react it with a molecule with 2 amine groups, diacamine, each molecule can react at both ends, linking them together in a long chain. This forms a polyamide. Famous examples are nylon 6,6, used in carpets and textiles, and Kevlar, incredibly strong stuff used in bulletproof vests.
Wow. Same idea for polyesters.
Exactly the same principle. React a diacid, or its derivative, with a diol, a molecule with 2 alcohol groups. You form repeating ester linkages, giving you a polyester. The most common example is PET, polyethylene terephthalate, which you know is Dacron fiber or mylar film, and it's used for clothing, plastic bottles, etc. Huge industrial scale chemistry.
Incredible application. What about reactions of amides? They're stable but not completely unreactive, right?
Correct. They can be hydrolyzed, but it's tough. Acid-catalyzed hydrolysis requires strong acid and prolonged heating. It breaks the amide bond to give the carboxylic acid and the corresponding ammonium ion Since the amine gets protonated under strong acid, it's effectively irreversible. And this brings us to maybe the most famous medically speaking story in organic chemistry. Beta-lactam antibiotics like penicillin.
Ah, Fleming in the moldy petri dish.
That's the one. Serendipitous discovery in 1928. Penicillin and related antibiotics like cephalosporins have a key structural feature, a four-membered ring containing an amide bond. This is called the beta-lactam. Now, normally amides are stable, but putting that amide into a strained four-membered ring makes it much more reactive, much more susceptible to hydrolysis. Ring strain wants to be relieved, and that's the key to how they work. The penicillin molecule uses its strained beta-lactam to acylate, essentially covalently bond to and deactivate, a bacterial enzyme called transpeptidase. Transpeptidase is crucial for bacteria building their cell walls. If you inhibit it, the bacteria can't build proper walls, they can't reproduce effectively, and the infection is stopped.
So the ring strain makes the amide reactive enough to disable the enzyme.
Precisely. It's a beautiful piece of molecular machinery. Of course, bacteria fought back. They evolved enzymes called beta-lactamases, whose job is specifically to hydrolyze that beta-lactam ring before it can reach the transpeptidase. That's the basis of antibiotic resistance for these drugs.
A constant battle. Okay, back to basic amide reactions. Basic hydrolysis.
Basic hydrolysis also works, but again, it's slow and requires heat. It yields the carboxylate salt and the free amine, also irreversible. And finally, reduction. This one is unique to amides in this chapter. When you treat an amide with excess LiLH4, it doesn't just reduce the carbonyl to an alcohol, it removes the carbonyl oxygen completely, converting the amide directly into an amine. The CaO becomes the CH2.
Oh, interesting. Completely different outcome than esters or acids.
Yeah, it's a very useful way to synthesize amines.
Okay, last derivative in the family. Nitriles. Yeah.
All right. We already saw one way to make them. SN2, reaction of an alkyl halide with cyanide ion. CN, great way to add one carbon and introduce the nitrile group. Remember, SN2 limitations apply best for primary or methyl halides. Another way is by dehydrating a primary MO. You can use reagents like phenyl chloride, SOCl2 for this. This is useful if you need to make, say, a tertiary nitrile that you couldn't get via SN2 reactions and nitriles. They can be hydrolyzed just like amines under either acidic or basic aqueous conditions. It actually goes through an amide intermediate first, and then that hydrolyzes further to the carboxylic acid or carboxylate under basic conditions. They also react with Grignard reagents. A Grignard adds to the nitrile carbon. Then when you add aqueous acid in the workup step, the intermediate enamine gets hydrolyzed to form a ketone. So nitrile plus Grignard gives you a ketone. Another good synthesis route. And finally, reduction. Just like carboxylic acids and amides, nitriles can be reduced all the way down to primary amines using excess LiLH4. The CN becomes a CH2NH2.
Phew. That's a lot of reactions. But seeing how nucleophilic acyl substitution ties most of them together really helps. So let's zoom out. Synthesis strategies. What are the key takeaways?
Okay, synthesis. When you're planning how to make a target molecule using the reactions from this chapter, you need to think about two main things. One, is the carbon skeleton changing? Are you adding carbons, like with Grignards or cyanide, or keeping it the same? Two, how are the functional groups changing? Are you converting one derivative into another? Are you changing the oxidation state, like reduction? Or are you changing the location of the functional group?
Right, and that reactivity ladder is key for functional group changes.
Absolutely. That map of reactivity in figure 20.1 of the textbook is crucial. Remember the order. Acid chlorides, anhydrides, esters, amides. Generally going down the ladder, more reactive to less reactive, is easy. Often just one step. React an acid chloride with an alcohol, bam, ester. But going up the ladder, less reactive to more reactive, usually takes more work. Want to turn an ester into an acid chloride, you typically have to hydrolyze the ester back to the carboxylic acid first, then treat the acid with phenyl chloride, often 2 steps. And note the specific limitations. This chapter doesn't give us a direct way to go from a carboxylic acid straight to an amide or a nitrile. You usually have to go via a more reactive derivative like an acid chloride.
Okay, that makes sense. What about the CC bond forming reactions?
We saw 2 main categories. Category 1, reactions where the functional group essentially stays put while you add carbons, like reacting an acid chloride with a Gilman reagent to make a ketone, or a Grignard to make an alcohol. The carbonyl carbon is still where it started. Category 2, reactions where forming the CC bond also involves moving or changing the functional group's nature, like making a nitrile via SN2 and then hydrolyzing it. The final carboxylic acid is 1 carbon further down the chain than the original halide. Or carboxylating a Grignard, the carbon you add becomes the carboxylic acid group.
So planning where the functional group ends up is important.
It's absolutely critical advice for planning synthesis efficiently.
Always think about the final desired location of your functional group when you're choosing your CC bond-forming reaction. It's almost always much easier and shorter to install the carbon skeleton with the functional group already in the right place, rather than building the skeleton and then having to do multiple, sometimes tricky steps later just to move the functional group around. Plan ahead.
Great advice. Lastly, how do we actually identify these compounds if we make them in the lab? Spectroscopy. Quick highlights.
Sure, spectroscopy gives us the fingerprints. IR spectroscopy is huge here because the carbonyl group, CO, gives a very strong absorption. The exact position tells you a lot. Acid chlorides are typically high, around 1,800 centimeters 1, and hydrides often show 2 peaks. Esters around 1,735, 1,745 centimeters 1. Amides are lower, maybe 1,650, 1,690 centimeters 1. Carboxylic acids themselves are around 1,710 centimeters 1. Conjugation usually lowers these frequencies a bit.
And the OH stretch for acids?
Yes, that's the other dead giveaway for carboxylic acids in IR. A very broad, sometimes messy-looking signal for the OH stretch, typically spanning from maybe 3,600 down to 2,200 centimeters 1. It often overlaps the CH stretches, super characteristic. And don't forget nitriles. The CN triple bond shows a sharp absorption around 2,200, 2,250 centimeters 1, usually medium intensity.
Okay, NMR.
13C NMR. The carbonyl carbon itself shows up way downfield, typically between 160 and 185 ppm. It can be hard to distinguish the exact derivative type just from this, but it confirms the carbonyl. Nitrile carbons are further upfield, maybe 115, 130 ppm, 1H NMR. The most distinctive signal is the acidic proton of a carboxylic acid, COH. It's usually very far downfield, often around 10, 13 ppm, and it's often broad. Protons on carbons next to the carbonyl, alpha protons, are also deshielded, typically appearing around 2.5 ppm. For amides, the NH protons can show up over a wide range, often 5.9 ppm, and can be broad.
Wow, okay, we have really taken a deep dive today. Carboxylic acids, their derivatives from smells and medicines to soap and Kevlar, and seeing how nucleophilic acyl substitution really connects almost everything. It's pretty fundamental stuff.
It really is.
Yeah.
And that's the take-home message, I think. Understanding why these reactions happen, the mechanisms, the electronic effects, it's so much more powerful than just trying to memorize dozens of reactions.
Yeah.
It unlocks that deeper understanding of organic chemistry, and you start seeing its impact everywhere. Pharmaceuticals, materials, biology. It's all connected.
So think about this. The next time you take an aspirin, maybe wash your hands with soap or even put on a polyester shirt, you're interacting with this whole world of elegant chemical transformations, all governed by the principles we've talked about today. What other everyday things around you are doing incredible chemistry, silently, that maybe you've never considered before? Well, thank you so much for joining us on this deep dive. Keep learning, keep questioning, and we'll catch you on the next one.